Okay, we're going to do this example here that you hopefully started previously, and then hopefully you'll have a better idea, hopefully, what's going on, I hope, right? All right, so let's take a look at this one here. I'll sit over here out of the lights so you can actually see the screen. All right, so once again, we have a couple of things going on here. First off, we do know it is a limiting reagent problem because they gave us the grams of this guy, which definitely from the grams we could get to the moles using the molar mass, which they were nice enough to give us as well. And they also gave us the grams here of our other reactant, which we can definitely get to the moles from as well. So again, that really is your big hint that it is a limiting reagent problem. It means that at some point you need to do, obviously, the limiting reagent sort of calculation. By the way, a also big misconception that people have when they do limiting reagent problems is it's always the guy with the smallest number of grams or something like that, and that is not the case. So if you have a limiting reagent problem, you actually do have to do some type of calculation to determine which one's the limiting reagent. You can't just look and go, that one's the smaller amount. That's going to be the limiting reagent. So keep that in mind. That's a very common sort of mistake. Once again here, we start out pretty much no matter what method you choose with the same couple of opening steps, which is we want the equation that's balanced, which it is. We then want to convert into moles. So we're going to do that first here. So we'll take our, I'll just do it here, our 2.46 times 10 to the 7 grams of TiCl4. If it was not provided to you, you would need to go to the periodic table to calculate the molar mass. But since it was, we will use it here. And that is going to give you a reminder to make sure you are using your exponent button, obviously, in this particular problem here. And you will get something like 1.2968 times 10 to the 5th moles of TiCl4. We're going to do the same thing for our magnesium, which is 1.13 times 10 to the 7 grams of magnesium, using the molar mass from the periodic table for magnesium, 2431 grams per mole. That gives us 1.13 to the 7 divided by 2431. Going to give us 4.648. We'll go 3 times 10 to the 5th moles of magnesium. Any questions so far here? All right, so once again, I'm going to do this using the ice table approach so you can again see how that works. And again, once again, if you learned a method previously and you really like to do it that way, you absolutely could still do it that way, and you should get, again, the same sort of answer. So with that being said, we're going to do our ice table here. I rewrote it. So we're going to start with our initial moles of each of these guys, and I believe that should be 1.296. I'll do a little bit rounding here. 8 times 10 to the 5th moles. And we got 4.6483 times 10 to the 5th moles of this guy. That's going to be 0 and 0 on that side of the arrow as my number kind of crossed over a little bit. Again, the most important part really of the ice table is the change part, since that really does take into account the stoichiometry. So we're going to do minus x because this is a coefficient of 1. We're going to do minus 2x because that's a coefficient of 2. Over here, that's a 1, which means this is going to be plus x. And over here, that's a 2, so that will be plus 2x. Any questions on that? So as I mentioned earlier, if you do not put those coefficients in, you pretty much didn't do the mole to mole part of it, which is kind of what stoichiometry is about. So you will get the wrong answer. At this point, we're just going to bring everybody down. We got kind of big numbers here, but 1.2968 times 10 to the 5th minus x. I can get rid of the moles for now, just to make it a little bit less of stuff in the way. minus 2x. This is going to give us x, and that's going to be 2x. Any questions on how to set up the table there? At this point, once you kind of bring everybody down, we can do those two kind of quick calculations to figure out which one's the limiting reagent. And we're just going to basically set each of these guys equal to 0. And obviously, this first one's pretty simple. It's straightforward. X would equal 1.2968 times 10 to the 5th. Here, this would be basically 4.6483 times 10 to the 5th equals 2x. Dividing by 2 will give us an x value here of 2.324 times 10 to the 5th moles. Any question on how we do that calculation there? Just basically solving for x. At this point, we compare the two x values, and this guy here is too big. It is the larger one. This guy is the smaller one. And that means that this will be our limiting reagent. So from that calculation, because we got the smaller x value, that means that this first guy here is going to be our limiting reagent. And by default, in this case, it is going to be the excess reagent will be the magnesium. Any questions on that there? Once again, this is helpful because that x value that you just got, which is in moles, so this x value right here is, again, every single x value that we see in the table, which allows us, again, to really solve for anything that we're looking for. So we'll start with what the question asks for, which is how many grams of TI. And if we do that, once again, we want to make sure we're using our smaller x value here. We can see from the table that the moles of TI equals x, which means we have 1.2968 times 10 to the 5th moles of TI. Using the molar mass for TI, which I wrote up there before we left there, was that 47? Was that 47 something? Where is it at there? 4787, I think. So from the periodic table, 4787 grams per mole is the molar mass of TI. And that will get us 1.2968 to the 5th times 4787. And that will get us something here, which we could kind of clean up at this point, of maybe 6.2. What was our original numbers there? 3. So we'll go 6.21 times 10 to the 6 grams of TI. That would be our theoretical yield, right, for our TI. Any questions on that there? The question was, right, what is the percent yield in this case? So to calculate the percent yield, that would be our actual divided by our theoretical times 100%. And again, in this problem, our actual was given to us that I scribbled all over. It looks like 5.42. 5.42 times 10 to the 6 grams divided by 6.21 times 10 to the 6 grams times 100%. And that would get us 5.42 to the 6 divided by 6.21 to the 6 times it by 100. And that's going to be 87.28. Not too bad. 87.28% yield. Pretty decent. By the way, when you calculate percent yield, it doesn't necessarily always have to be grams divided by grams, as long as they're the same unit. So you could do moles divided by moles if you wanted to, or as long as they are the same units on top for the actual and bottom, you could divide the two. Question on that there? Yeah. Percent error is different. Percent error is when you take your experimental error minus the true value divided by the true value. So it's very common people get those two things confused. So percent yield is how much product or how well you did for making the product. Percent error is overall how good you did in terms of what the true value or answer should be. So percent error, we want low, which means we're not very far off. percent yield, we actually want high, which means we actually yielded a lot in our reaction. We didn't have a bunch of side reactions or lost a lot of product along the way. Yeah. Other questions? So again, just to show you sort of the benefit here, if we also wanted to know how much magnesium chloride we would have produced, we can go with the moles of magnesium chloride, which from our table is 2x, which means we would take 2 times our x value that we had. And that would get us here about 2.5936 times 10 to the 5th moles of our magnesium chloride. We could use the molar mass of magnesium chloride, which would be 2431 plus 2 times 3545, which is the chlorine. And that would get us about 95.21 grams per mole from the periodic table. So taking our number there, 2.5936 times 10 to the 5th. Using our molar mass here of 95.21 grams per mole. Gets us 2.5936 to the 5th. About 2.47 times 10 to the 7 grams of magnesium chloride here would be produced. So again, relatively easy. We can figure out how much of the other product was produced in this case by just figuring out the molar mass and using our ice table. We also, again, if we want to know how much of our excess reagent was left over, we could go back into that table there. And I'll do that right here, maybe. I'll just kind of do it right there. So if we go back to our table and we would take our excess reagent and we would take 4.6483 times 10 to the 5th minus 2 times our x value. And this would tell us that at the end of this reaction here, we would have about 2.0547 times 10 to the 5th moles of magnesium left over, which if we want to know grams, we could times that by our 2431 grams per mole, which is the molar mass of magnesium. And we would have something like 4.99 times 10 to the 6 grams of magnesium left over. So again, within a couple of steps, we could figure out how much of the excess reagent is left over. We started with 1.13 times 10 to the 7 grams of it. So we have a good amount still left over in this case. So as you can see very quickly, pretty much can answer any type of question that's typically asked in these sort of stoichiometry or limiting reagent problems. First off, any questions on any of the calculation part there? Couple of things I will say is it is probably best to do a ice table approach if you choose to do it that way in a limiting reagent problem only. In a basic stoichiometry problem, it's just easier just to do the 4 steps like we did at the beginning, because you already know what is the limiting reagent. It's whichever one's given to you. That's a reactant if you're going to figure out how much product. So I would use this specifically for limiting reagent problems using the ice table approach. And again, just use those 4 steps for a basic stoichiometry problem. Any questions on any part about there? All right, let me scroll this through, which I think is, again, the alternative approach might be here. So in case you want to look at it later, this again is figuring out, do you have enough of one reagent to use up the other reagent? So again, if you want to look at it here, That is what the calculation on the bottom is. The bottom here is the alternative approach that says if I want to use up all my TiCl4, I would need 2.6 times 10 to the 5 moles of magnesium. I would then do a comparison to how much I'm starting with and see if I have enough. And if I do have enough, then that's the excess reagent. If I do not have enough, then it is the limiting reagent. And in this case, we do have enough of magnesium, which tells us that like we saw in the other approach, the TiCl4 is the limiting. And again, at that point, we would use the starting amount of our limiting reagent to figure out how much of our product we would produce. And then we could do our percent yield calculation here. So in case you want to look over an alternative approach, that is it right there. Any questions on limiting reagents, percent yield, all that kind of stuff? All right, we will lay it up there for now. We will do a couple more examples, obviously, next time.